Hello friends, welcome to this fifth video on the series of graph theory. This video will cover about what is meant by path, a circuit, a connectivity, and how we can see graphs with various kinds of path and connectivity, and we can calculate the length of them. Come on, we will get into the definitions. What do we mean by a path? A path from a vertex B1 to a vertex Bn in a graph G is going to be an finite alternating sequences of vertices and edges that begin with a vertex and with end with an vertex. Okay, so if we are going to have a V1, a V2, a V3, one V4, a V5, a V2, and then again a V1, and we go to V6. So what happens over here? The vertices and edges over here are going to be alternatively traversed for, or we have a sequence which is going to have alternatively a vertex and edge, vertex, edge, vertex, edge, and so on. It starts with a vertex and it ends with a vertex, in which case we call this to be a path. And now, what is meant by a simple path? So, when we are traversing this path, if the edges become distinct in nature, what do we mean by edge? The line that connects any two vertices is referred as an edge. If this edge is going to be distinct, that is, you are not going to travel the same edge two or more times, then you call this to be a simple path. Then you traverse every edge of it only once, then you call the path to be a simple path. Next one, what do you mean by a cycle or circuit? If the initial and final vertex of the path are going to be the same, so you begin with V1, you go to V2, you go to V3, and you return back to your V1. So now this is going to be a walk where you start at a vertex and you end at the same vertex. Then this path will now be referred by the name circuit or a cycle. And if there is no repetition of edges in the same, then this circuit will now be referred by the name called as simple cycle or simple circuit. Now we will take an example. Before that, what do we mean by the length of a path? The length of the path is going to be the number of edges that is going to be present either in this path or in a cycle. So the number of edges that are present in the path or cycle will be referred as the length of the path or length of the cycle. Consider this example over here. We start with F1. We move to E6A. We are going E6A. We are moving from E8. We are reaching D. We are moving along E3. We are reaching C. We are moving along E2. We are reaching B. We are moving along our E9. And now again reaching our D, and we are moving along our E8. We are moving with A. We are moving with our E1, a B, and a E9, a D, and a E4, and a E. So we are going so many traversals or alternating sequences of vertices and edges. So in this case, what do we refer as? This sequence of vertex, edge, vertex, edge, vertex, edge, which begins with an vertex and that ends with a vertex, will be called as a path. Now what is going to be the length of this path? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges are present in this path. So the length of this path is going to be 9. But can we term this path to be a simple path? No. Why? Because you can see that the edge E8 happens over here and the edge E8 also happens over here. In a similar fashion, we can say that the E9 is present here and E9 is also present here. So there are going to be repetition of your edges. So we cannot call this path as a simple path. But now you look into the second example where we start with A, E8, A, we are moving to E8, we are moving and reaching D, we are going along E9, we are reaching B, we take the E2, we are reaching C, we take the E3 and we are reaching D, we are taking E4 and we are reaching E. All the edges are being traveled or walked along exactly one. It begins with a vertex, ends with a vertex, and we see E8, E9, E2, E3, E4. There is no repetition of edges. All the edges are distinct, in which case the path which we have traveled now will be referred by the name simple path. What is the length of this path? The length of this path 1, 2, 3, 4, 5. 5 edges are present. So the length of this simple path is 5. Now what do we mean by a cycle? It has to start with a vertex and end in the same vertex. Say it starts with A, it ends with A. Okay. A, it moves along E10, it goes to E, next E4, it goes to D, and then you move along E9, you reach your B, you take your E7, you come to E, you take your E10 again back and reach your A. So this is going to be a cycle. This cycle has 1, 2, 3, 4, 5. 5 edges, and so the length is 5. We also notice that the edge E10 over here has been traveled twice. So this is not a simple cycle. So what is meant by a simple cycle? Where every edge is going to be distinct. You begin in a vertex and you end in the same vertex. Like you stay with A, you take your E8, you reach your D, you take your E3, you go to your C, you go to your E2 and take your B, you take your E1 and then you reach back to your A. So A, D, C, B and back to A. Now you see that there is no repetition of edges, and this will now be referred by the name called as simple cycle. And what is the length of this cycle? This is going to have 4 edges, and so the length is going to be 4. You can find more than one cycles inside the same graph. It is not that you will have to consider all the edges or all the vertices when you are talking about a path or talking about a cycle or a circuit. Okay, so you may ignore certain values which is going to be vertices, you may ignore certain edges, but still that can be referred as a path if it is going to have an alternating sequences of vertices and edges, and if it is starting and beginning in the same point, then you call it by a cycle. Next, we will see what is meant by a connected graph. An undirected graph is said to be connected if there is a path between every pair of distinct vertices. You take any two distinct vertices, you will be able to find a path to it. So when I take A and F, I go from A, I go to B and I go to F. There is a path. Okay, let me take A and D. I go to A, I go to B, I go to C, I go to D. There is a path. Can you talk about B and D? Yes, from B to D directly there is a path. Can you talk about C and E? Yes, C, D, E is a path. Can you talk about C and F? C, B, F or C, D, B, F. There is a path. So you take any pair of distinct vertices. If there is a path, then you call the graph to be connected. Now, what do you mean by disconnected graph? If there is not going to be a path between any pair of given distinct vertices, then you call the graph to be disconnected. Now, this is going to be a graph. Now, you see the point B and F. Are you able to reach from the point called as F to B? No, there is not a path or an edge that is going to happen over here. Will you be able to move from D to G? Will that be possible? No, we don't have any connectivity over here. So I may not be able to move from D to my G. So this kind of graph will be called as disconnected graph. A disconnected graph is actually the union of two or more connected subgraph. So what happens? Each one of them now becomes a subgraph, but they don't have a vertex which is going to be in common. They have no common vertex. So this as such is going to be a subgraph, and this as such is going to be a subgraph, and they are going to be the subgraph of the original graph called as G. There is no common point or common vertex that is going to be appearing between these two subgraphs. These disjoint components, that is this individually and this individually, are now referred by the name called as components. So each of these subgraphs which are connected among themselves will be referred by the name connected components of the graph. So this becomes one component and this becomes my component number 2 for this graph G. Now let us look into two theorems that talk about connectivities and paths. If a graph G is connected or disconnected, it has exactly two vertices of odd degree, then there is a path that joins these two vertices. So if you have exactly two vertices of odd degree, then you can find a path between them. Okay, are we having any vertex of odd degree over here? Okay, we will see. What is the degree of A? Degree of A is going to be 1. This is going to be degree of B, F, which is 1. And 1, 2, 3, 4, 5. So this has odd degree. 1, 2, 3. This is going to be of odd degree. 1, 2, 3, 4. 4 odd degrees are present. So if it has exactly two vertices of odd degree, there is going to be a path. But this has more than that. But still it has a path. So we will see if it is going to have a path, if it is going to have exactly two vertices over here. Now, if there is a question like, consider the following graph. Do you think there is going to be a path existing in this graph? Yeah, we will see. If there are going to be exactly two vertices of odd degree, there is a path between these two vertices. Okay, so we see that over here, this is going to be of 2, 2, 1, 2, 3, 4, 1, 2, 3. Okay, here you have a 1, 2, 3, 1, 2, 3. Here you have a degree 1, a degree 1. So this also has a going to have a vertex which has, there are going to be 4 vertices of odd degree, and so we will be able to find a path between these two quantities. Now, is there a path between these two vertices? Yes, obviously we can start over here. From my F, I can go, if I want to connect say F and G, which is going to be of odd vertices. Will there be a path? Yes, F to D, D to E, E to G. There is going to be a path between these two vertices. Now D and F is going to be of odd vertices. Is there a path between them? Yes, directly there is a path between them. There is a D, there is a E. Is there a path between them? Yes. They are both odd vertices and there exists a path between them. F is here, E is here. Is there a path between them? Yes, there is a path. So, if you have exactly two vertices of odd degree, there is going to be a path joining these two vertices. Now, over here, if it has exactly, so obviously over here, there was not exactly 2, but there were 4 and we were able to find a path. Now, if it is restricted to just 2, will there be again a path of such kind? Yes, we will see. This graph has over here degree to be 3 and over here also degree to be equal to 3. So, it has exactly 2 vertices of odd degree. And are you able to find a path joining these two vertices? Yeah, we can travel from A, B, C, D, in which case how to connect these two vertices? I can move from B, I can go to C, I can go to D. This is going to be a path. I can directly move from B to D. This is a path. I can move via B, A, D and a B. So this is going to be a B, a A and a D. This is going to be a path. So when you have exactly two vertices of odd degree, for sure you will be able to find a path between these two vertices. The second theorem says the maximum number of edges in a simple disconnected graph of k components and n vertices is going to be n minus k into n minus k plus 1 by 2. Notice this is going to be the maximum number, how much full to the fullest extent, how many edges we can draw for a disconnected graph. So if it has n vertices and k components, it has n minus k into n minus k plus 1 by 2. Now consider our disconnected graph over here. So our disconnected graph has how many vertices? Vertices are going to be 1, 2, 3, 4, 5, 6, 7. 7 vertices are there. How many components are there? Components are going to be, this is going to be component 1 and this is going to be component number 2. So they say maximum number of edges in this disconnected graph has to be n minus k into n minus k plus 1 divided by 2. So this will be equal to, this is my n, so n minus k, 5 minus 2, so this will become 5, and 5 minus 2 plus 1, so 6 divided by 2. 6 pies are 30, 30 by 2 will be equal to 15. Maximum how many edges you can have over here in this graph? You can have 15. How many edges we do have? 1, 2, 3, 4, 5, 6, 7. Obviously 7 is going to be less than 15, and so the theorem is going to hold true. So I can have maximum of 15 edges that can be present between these two disconnected or component wise graph. So this is going to be the second theorem for us. Now coming to the problem, we will find the number of paths of length 4 from the vertex B to the vertex D in the graph given over here analytically. We will also find, we will have to first find the number of paths, and we will also have to identify these paths from the given graph. Now how to go about this problem analytically? So the way is through our matrix method. So what does our matrix method say? So let me first write what is going to be the adjacency matrix for this graph A, B, C, D and A, B, C, D. So we are now being given with a directed graph. What do you mean by directed graph? There is going to be direction. From A to A, is there is going to be an edge? No. So this will become 0. From A to B, is there an edge? Yes. So we mark this as 1. If there is an edge, put 1. If there is no edge, put 0. So a matrix of any graph will have just entries 0s and 1 for a simple graph. Okay. If it is a loop, then your entry will be equal to 2, because a loop is one that starts and ends at the same point. Okay. So that also will be for a directed graph and not for an undirected graph, not for a directed. So now from A to B you have 1. A to C, do you have 1 from A to C? No, it is only from C to A. So this will become equal to 0. A to D, no, it's only in the reverse way. So this will also become 0. B to A, no, you don't have 1. B to B, no, you don't have 1. B to C, yes, we do have 1. B to D, yes, we have it from over here. Next C, C to A. C to A, yes, we do have 1. C to B, yes, we do have 1. C to C, no, we don't have 1. And C to D, is there an edge? Yes, we do have. So this will become 1. Now from D, D to A, yes, we do have. D to B, no, we don't have. D to C, no, we don't have. And D to D, no, we don't have. So this matrix which is formed is called by the name adjacency matrix. Okay, so this is the adjacency matrix of the given directed graph G. Now we need to find the number of path of length 4. So how much is going to be the length required? We need it of length 4. So if I am going to mark this matrix as A, the requirement is going to be for length 4. then what we need to do is we need to compute a to the power of 4. Now this is my given a. In the next stage, what we will do, we will compute a square. What is a square? 0, 1, 0, 0, 0, 0, 1, 1. This is going to be 1, 1, 0, 1 and 1, 0, 0, 0. Now this you do one more time, a matrix multiplication with 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1 and 1, 0, 0, 0. So the final answer for your a square has to be 0, 0, 1, 1. You will have this as 2, 1, 0, 1, 1, 1, 1, 1 and 0, 1, 0, 0. This is my a square. What will be my a power 4? My a power 4 will be a square into a square. So 2 copies of a square. 0, 0, 1, 1, 2, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 0. One more time, the same copy you take 0, 0, 1, 1, 2, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 0. So when you multiply these two matrices, you will have this as 1, 2, 1, 1, 2, 2, 3, 3, 3, 3, 2, 3, 2, 1, 0, 1. So this is going to be my matrix entry for A4. Why did we do A4? Because they are asking us of length 4. So do it A4 time. If they are asking for length 3, then you compute till A cube, which is a square into a. So now this is going to be my vertex A, B, C, D. A, B, C, D. Length 4 now has been obtained. From where to where I need to move? From vertex B to vertex D. So you start from vertex B and you need to move to vertex D. Vertex B to D. Now see, what is the number present over here? 3. So this says that there are going to be 3 paths of length 4 from your B to the vertex D. So what was the first question? They are asking us the number of path. So how many paths exist from B to D of length 4? So the number of path of length 4 from B to D is going to be 3. Now the next question is, we need to identify these paths. So we now know that there are going to be 3 paths that exist from B to D of length to be equal to 4. Now what are they? So let us first chart them out. Number 1, let me start with B. I go to C, I go to B back again, I go to C and I go to D. B, C, B, C. So 1, 2, 1, 2 and then I come to D. So this is going to be of length 4. Number 2, let me start with B, C, A, B, D. B, C, A, B, D. This is also going to be of length 4. Number 3, let me start with B, D, A, B, D. B, D, A, B and again D. So this is going to be also of length 4. So this is the maximum quantity I can find, and these are the exact values for a 3 path of length 4 from our B to D. So hope the concept was clear. Given any graph, find what is your adjacency matrix. Notice only a adjacency matrix will have entries as just zeros and ones. But over here we are now computing only powers of a squares and a power 4. So here you can have entries apart from zeros and ones also. Don't think that we need to have only 0 and 1. Why is this 2 coming? Why is this 3 coming? This is not our adjacency matrix. This is only a matrix multiplication or computation which we have done here. So this can have numbers apart from zeros and ones. Only in the case of your adjacency matrix, if there is an edge then you mark the matrix entry as 1. If there is not going to be any edge, you mark the matrix entry as 0. So only zeros and ones will be present in an adjacency matrix, but for the other cases you may have other values also. Hope this video gave you an idea of what was meant by an path, a cycle or a circuit, what is meant by the length, what are going to be connected graphs, what is going to be disconnected graph, and how to find a length of a given quantity from a particular vertex to the other vertex and the path defined for them. Happy learning, keep learning. Thank you.